Hi, I'm Mrs. I'm presenting my individual TMA report, BUS105 Statistics. Student number Y0706914. Let's not delay any further. Moving on to question 1. We plot 3 graphs using SPSS software of selling price versus house size, number of bedrooms, and number of bathrooms. We ignore the geographical locations. In all 3 graphs, there's a single regression equation. In all 3 graphs, R squared determines what exactly is R squared. It shows the variability which is explained by the equation. When we plot it versus housing size, R squared is 77%, versus bedroom 67%, versus bathroom 69%. In all 3 graphs, there's a relationship between its independent variables and dependent variables, x and y. All 3 shows a positive slope and a good degree of linearity. How do we interpret? Here's an example. Every additional 1 bedroom leads to an estimated increase of 90,730 in selling price. Moving on to question 2. We let Y be the estimated selling price of a house. And a general equation would be Y equals to B0 plus B1x1 plus B2x2 and so on and so forth. B0, 1, 2, and 3 used to represent beta naught 1, 2, and 3 as they are point estimators used in a sample test. Using the software again, we compute the data and we get many relevant tables, one of which coefficient table. From the coefficient table, we can find the coefficient of each parameter. The equation we get would be Y equals to minus 47.342 plus 6.02 x1 plus 23.035 x2 plus 27.029 x3. How do we integrate this equation? One increase in bedroom leads to 23,035. One increase in bathroom leads to $27.29. And one increase in housing size leads to 6,020. This is only applicable if all other independent variables are held constant if one was changed. We get the interval table and model summary table. From here, we can get regression of square, residual regression, R square, and R alternate, F and significance, mean square, degrees of freedom. Let's test the system. We perform manual calculations using Appendix B and the formula from the textbook, and it all agrees with the results from the software. However, we get it slightly away. There's running off error and human error. It is almost impossible to perform such calculations as it involves heavy metrics. Next, we perform the F test for overall significance. Step 1, we develop the hypothesis H0 or the beta is equal to 0. H alternate, at least one is equal not to 0. We develop the group of rejection and we compute based on data from the software and from Appendix B from our textbook. With all useful data discovered, we can conclude from the F test to reject H0 because F 39.202 is more than 3.07, which is found in Appendix B, and p-value is less than 0.05, which can be found in the coefficient table. Next, we test for the individual significance. We use the t-test. Again, same steps, we develop the hypothesis H0, B1 is equal to 0, and beta 1 is not equal to 0. We develop the group of rejection And once again, we compute. And again, finally we conclude that we do not reject each node using the T or T-value approach. This is because 2.05 is lesser than 2.08 and 0.054 is greater than 0.05. Why is there a conflicting result? Why does one test say we reject and why does one test say we do not reject each node? This is because there is multicollinearity. There is correlation between the independent variables. This is especially so when VIF is greater than 5 for the housing size. Technically speaking, housing size is affected by the number of bedrooms and bathrooms. We perform the residual analysis from the PP plot. We can see that the residuals do not deviate from the 45 degrees line. And from the scatter plot, the residuals are randomly scattered in a horizontal band from -2 to 2. What does this show? All three assumptions are not violated. The three assumptions are the independence of errors, the normality of errors, and the variance are constant. Homoscedasticity. Let's move on to question 3. Question 3 is similar to question 2, except there is an additional variable, a dummy variable. We assign it to be 0 if the house is in the west and 1 if the house is in the south. Again, we use the software and the equation will be y equals to 21.505 plus 5.162x1 plus 24.799x2 plus 26.705x3 minus 21.706x4. Again, we integrate the equation. However, if the house is in the south, which means x4 equals to 1, the price is expected to go lower by $21,706. The way we interpret the equation is similar to question 2. I will not go into much details as it is really similar. Again, we have ANOVA and model summary tables. We do not need to do manual calculations. We can truly trust the auto computation. And again, S-test and T-test results in conflicting results because VIF is greater than 5 again in housing size. The residual analysis is not violated. We substitute the values given in question 4 into the multiple regression equation and we get the answer is $199,218. Application of this equation will be extremely useful in surveying and civil engineering. This is especially so when we use arterial light to calculate and the balance of human error. This best fit method helps to offset errors from chain surveying. Thank you for watching.